Hello and welcome to the next lecture of Machine Learning for Core Engineering Disciplines, an NPTEL course. In today's lecture, we will take it forward from last time where we discussed the concept of singular value decomposition and principal component analysis, and specifically today's lecture will take us into the world of clustering algorithms. Clustering, as you know, is another sort of unsupervised learning wherein you try to partition your data set into various clusters based on how much the data points are similar to each other and how different they are. And this can be very valuable, right, because you want to find hidden patterns in your data set. Let us say you are trying to find out which molecules are similar to each other. You work in a drug company and you want to know that, or if you have sort of operating conditions of manufacturing plant, then you want to find out what are the combinations of operating conditions which lead to a good yield or good success rate, right. So, those are the kinds of circumstances when you may want to use these kind of clustering algorithms. So, let us go ahead and get started. So, the topic for today is clustering algorithms in unsupervised learning. Okay. So, what exactly is clustering? Okay. So, clustering is a form of unsupervised learning wherein we split, right, or partition the data set into various groups or regions which are called clusters, with a goal to understand the data structure, in terms of the similarity and the dissimilarities between various data points. Okay. And this can also help you in some way do better supervised learning. For example, you can apply a different supervised learning algorithm within each cluster, given that each cluster has more points, right. You can't really apply supervised learning when the number of data points is too low within a given cluster. So, within each region the points are more similar. So, when we talk about these similarities and dissimilarities, so within each cluster the points are similar to each other than to points outside that particular cluster, and between different clusters the points are more different from each other compared to points within the same cluster. Okay. So, this is essentially what clustering is, and it can be done through various algorithms. We will learn some of these algorithms in this course. So, the first algorithm I want to introduce for doing clustering is called k-means clustering. okay. And here, right, it is a clustering algorithm that divides data points into k clusters. So that is why the name has a k, just like k fold cross validation, there are k folds. Here in k means clustering there are k clusters, right, with each point assigned to the cluster which is closest, whose mean is closest to that point, right. So that is why the name mean comes in the name. So there are k clusters with each point assigned to the cluster whose mean is closest to that point. So what would this look like pictorially? So for our simplified discussion, let us consider the case of just two features being there, right. So there are two features in our simplified discussion. So there is feature 1 and there is feature 2, okay. And let us say these are the data points. I am already going to be drawing them so that they are colored differently and symbols are also different, right. So this is, let us say, cluster 3, and then there is cluster 1, let us say here, and there is cluster 2 somewhere here. Right. So this is sort of a made up example. So I have taken these clusters to be very different, but when you are starting out you will not know how these clusters are distributed in the feature space, right, because you have p features and it is very complicated to visualize anything beyond 3 dimensions for humans. So you will not really be able to visualize it, but when you find the distances, right, the Euclidean distances used in k means clustering, you will figure out which points are similar to each other and which are different, right. So there are 3 clusters here and you need to find out the mean of every cluster, right. So this, for example, could be the mean of this cluster, this could be the mean of this cluster, and somewhere here is, for example, the mean of this cluster. So to successfully carry out the k means clustering algorithm, you need to define the mean, or you need to know the mean of every cluster. So let us say this is m1 vector is the mean of the first cluster, m2 vector is the mean of the second cluster, and m3 vector is the mean of the third cluster, right. So in this notation, mj vector is the mean of the jth cluster, and for a point in cluster 1, for example, m1 vector is closer to it than m2 and m3. That is how this works, right, that is the way it works. So if you take some point here, right, this distance will be shorter than this distance and this distance. So you can see that the distance from cluster 1's mean, so let us say that is L1, L1 is shorter than L2 and L3. So that is how this point here was decided to be put in cluster 1, and this kind of a logic can be used for the other clusters as well and other data points as well. So I hope you get a physical feel for how this clustering really works and how clustering is done. Now how do we do it algorithmically? So for that we have to first define something known as the within cluster sum of squares, and then look at an algorithm that will take you towards lower and lower values of this within cluster sum of squares. So, given n data points, right, and I am representing by x1 vector, x2 vector up to xn vector, and you know that these are all row vectors. When you have the X matrix, then every row is a data point, every column is a feature, right. So, the goal is to create k clusters, and obviously k is less than or equal to the number of data points. If k is equal to n, then you have as many clusters as data points. It is not very useful. What it tells you is every point is unique, but the whole idea was to understand which points are similar to each other. So, that defeats the purpose. So, typically you want k to be much lower than the number of points, so you get some insight into the similarities and dissimilarities, right. So, the goal is to create k clusters denoted as C1 cluster 1, C2 cluster 2, all the way up to cluster k, so as to minimize what is known as the sum of variances within each cluster. So, that is how the points are similar to each other, because you have minimized the sum of variances within each cluster. So, the points within each cluster are more similar to each other, and this is called the within cluster sum of squares. Right, and abbreviated as WCSS. Okay. So, WCSS is given as sum over the clusters j equals 1 to k, and then you look at all the points which are there in that particular cluster. So, x I going from 1 to n, but only those i's which are part of the cluster Cj, right. So, this is set notation and this is the belongs to symbol. So, x belongs to the set of points in cluster J, Cj, and you take the distance squared or norm squared between xi and mj. Okay. So, this, as you know, right, the sum of squared is basically the number of points minus 1 times the variance, right. So, it is some estimate of the variance. It is not been normalized, but it nevertheless is a measure of the variance. So, here mj, it denotes the mean or centroid of cluster Cj, and of course, this I is an index for the points, and this means that the ith point is belonging to the jth cluster. Okay. So, the assignment of clusters can be written as a minimization of this within cluster sum of squares. Okay. So, that is you are trying to find the clusters, right, the argument, right, which is the set of clusters C1, C2 up to Ck, right, which minimize the within cluster sum of squares. So, it is the argument which leads to the minimum value of the WCSS, and the arguments we are varying are basically the clusters themselves. So, j is equal to 1 to k, some I going from 1 to n, where xi vector belongs to the jth cluster, xi minus mj norm square. Okay. So, this is essentially the mathematical representation of what is happening when you do k means clustering, and it is clearly visible that you are using the square of the Euclidean distance here. Of course, this distance, like I said, is in p dimensions, it is not in 3 dimensions, because each data point has p features. Okay. So, this is what we have to do, but how is it achieved? So, this is done algorithmically. So, the algorithm for k means clustering is as follows. Okay. There are essentially several steps to be followed. The first step is the initialization of the clusters, right, because when you start you do not know what these clusters are, how should you take these clusters, but you know that you have to create k clusters. So, how do you create k clusters? There is two choices, one of two choices that you use. So, either k of the n data points are randomly chosen to be the cluster means for the first iteration, and let me denote these means as mj1 vector, right. So, there is for every cluster you will have a mean, and the superscript parenthesis 1 says that these are the initial guesses, and yeah, you could even write this as mj0, right, if you wanted to indicate the start of the algorithm. So, this is one way to choose the initial locations of the clusters. The other way is essentially each of the n points is randomly assigned to k clusters, to one of k clusters, and the cluster means are computed. Okay. So, in the first case, right, the k data points are themselves the means. So, you do not need to compute the means. In the second case, each of the n points is randomly assigned to k clusters, and therefore, you do need to compute the means, and these can be very easily computed. So, essentially the mean of the jth cluster at the 0th iteration is essentially the number of data points that have been assigned to the jth cluster by this random assignment, and you sum over all the points that belong to this cluster. So, xi belongs to the set j, and then you just sum over the vectors xi, and you do this for all the clusters j equals 1, 2, 3 all the way up to k, right. So, I hope this makes sense, right, and this is where some randomness is there in the algorithm, as in most ML algorithms, right. In supervised algorithms, that was coming from the train test split, right. You had to do the train test split randomly, and of course, if you do gradient descent, then the initial set of model parameters, they are also randomly chosen. Hyperparameters are in some sense also randomly chosen, although you do grid search. So, here again in unsupervised learning, you have some randomness, and there is a random state that you may have to specify in scikit-learn. Okay. So, this is the initialization phase, wherein you have initialized the k clusters, and then you sort of check, right, where each point belongs, and then you may have to change that and check whether the assignment of the clusters changed or not. So, let us go to the next step in the algorithm. So, the next step in the algorithm is the assignment of points to clusters, right. So, we just initialize the cluster centers. So, in assignment at the lth iteration, each point xi is assigned to the cluster Cj with the nearest mean. Okay, and that is determined as follows. You can write it in simple mathematical notation as follows. So, Cj L, right. So, this cluster is formed by all those points which are closer to the centroid of that cluster compared to the centroid of any other cluster Q. For all data points and clusters where of course j is not equal to q. So, essentially you are saying that the distance between the ith point and the jth cluster must be lower than the distance between the ith point and the qth cluster. So, that is when, right, those points, right, will form those xi will form the jth cluster, right. So, to even further clarify this, you can say that this essentially equals all the xi vectors such that, right, this distance metric is followed. Okay. So, I hope this makes sense to you. Here this first term is the distance between xi and mean of the jth cluster, and this here, as you may have guessed, is the distance or distance squared, really I should say, between the point I and the mean of the qth cluster. Okay, so, this is where you are reforming the clusters based on the means that are computed, right, in the previous iteration. Okay. And now what we can do is let us say that these instead of CJL I should really say CJL plus 1, right, because you are updating the clusters. Okay. And now you can compare how these clusters changed between the two iterations. What were the clusters at the previous end of the previous iteration and what the clusters are now. So, that is essentially checking of convergence. Okay. So, the current or latest assignment of points to clusters is compared to the assignment at the end of the previous iteration. So, if the assignment of points does not change, the algorithm terminates. Why? Because if the assignment of points does not change, the means do not change, and the assignment will remain the same even if you repeated the algorithm. right. However, if the assignment of points does change, then the means have to be recalculated. So, if instead the assignment of points to clusters has changed, we recompute the cluster means. Okay. So, here your mj l plus 1 is recomputed, right, using the cluster information at the end of the previous iteration, right. So, you know that you are just taking the average, right, position in terms of the features of the points in the jth cluster, right. And again I want to remind you that this is the number of points, right, when I put the absolute value sign, that is the number of points assigned to the jth cluster. So, this is the number of points in the jth cluster. So, once the means are recalculated, then you go back to the assignment phase, right. You again do the assignment and then you keep on repeating this procedure till convergence is achieved, right. So, subsequently the assignment step, which is step P, is repeated till along with C till convergence is achieved. Okay, so that terminates the k-means algorithm, and I again want to emphasize that there is some randomness in this algorithm. So, this is an important note that the final assignment of clusters to points or points to clusters, I mean whichever way you want to look at it, depends on the initialization, right, procedure and random state chosen. So, essentially you find only a local minimum of the within cluster sum of squares. So, therefore, you only converge to a local minimum of the within cluster sum of squares, right, and this leads to some degree of randomness in the machine learning model, okay, in this unsupervised learning. Okay. So, this brings me to the end of this particular lecture. In today's lecture we introduced the concept of clustering, and we showed the algorithm for k-means clustering, which is a method to partition your n data points into k different clusters based on the Euclidean distance. We also discussed that this leads to a local minimum in terms of the within cluster sum of squares, which is a measure of the variance within of the data points within each cluster. What we will do in next class is we will discuss a little bit more on how the number of clusters is chosen. Then we will discuss something known as k-medoid clustering, which is slightly different from k-means clustering. We will also discuss density based clustering, which has become popular in recent years, right, for better use cases. And finally we will go on to other non-linear dimensionality reduction methodologies, and with that we will hopefully complete the concept of unsupervised learning. So thank you all for joining today. I hope you had a good time and see you next time.